of Lima. Lima Energy at work. Lima Energy products at work around the world. Meeting critical electrical demands at sea and in agriculture. Meeting standby electrical demands in hospitals, elevators, and on the world's pipelines. And more, people have grown to depend on Lima generators because whatever the demands, under the most severe circumstances, Lima generators perform. Today's Lima generators are a result of development programs spanning several years, thousands of test hours, and extensive field experience, making Lima one of the most highly respected generators in the world today. Maintaining these generators within their design specifications for application satisfaction, dependability, and long life requires a basic understanding of various generator concepts. This presentation is just one more example of Lima's dedication to its customers. During the next few minutes, we will be reviewing the basic fundamentals of magnetism, electricity, and electromagnetic induction, as well as reviewing the basic generator components and generator operation. We will not be concerning ourselves with the mathematics or physics necessary for an in-depth understanding of the design engineering of these machines. Instead, we'll be concentrating on those electrical concepts necessary for understanding generators. The surfaces of magnets are referred to as pole faces. A magnet establishes a magnetic field or field around itself. This field is referred to as lines of flux. These lines of flux are said to leave the North Pole, travel, and re-enter the South Pole of the magnet. The strength of the magnet is defined by its number of flux lines, or its flux density. As you know, permanent magnets are usually made of hard metal, such as steel. Once the metal has been introduced to magnetism, it will retain magnetic properties. The one disadvantage of a permanent magnet is that its field cannot be varied or controlled. It is said to have a fixed value of flux density. Electromagnetism and electromagnets, on the other hand, are the core to understanding generators, since they have the ability to vary their flux density or electromagnetic field. In 1819, Professor Ørsted discovered that when an electric current passed through a wire, a magnetic field was produced around the wire. The magnetic field around the wire is called electromagnetism. It was also discovered that the direction of the magnetic lines was dependent upon the direction of the current flow through the wire. The magnetic field formed around a single wire is relatively weak, even if the current flow is increased. However, if the wire is formed or wound into a coil, the magnetic field becomes much stronger. If a piece of magnetic material such as soft iron is placed within the coil, the magnetic properties of the coil are tremendously increased. This increase in magnetic strength of the coil is due to the greater permeability of soft iron as compared to air. Permeability of material is the ease with which lines of flux pass through the material. A coil wound around a core of magnetic material is called an electromagnet. The strength of an electromagnet is determined by two factors: the number of turns in the coil and the amount of electric current passing through the coil. Any magnetism remaining in the core after the current flow has stopped is referred to as residual magnetism. In 1831, Michael Faraday was credited with what to many is considered the most important scientific discovery of all time. He discovered that when a conductor moved through a magnetic field an electrical voltage was produced in the conductor and caused an electric current to flow in the conductor. This phenomenon is called electromagnetic induction, and the voltage produced in the coil is said to have been induced into the coil. Today, all electric motor, generator, and transformer actions are based on this principle. Faraday further discovered that the value of the voltage induced by the moving field was dependent on three factors. 1. The number of lines of flux being cut by the coil. 2. The relative velocity of the coil to the field. And 3. The number of loops of wire or turns in the coil. So far, we have been discussing relative velocity, or the movement of the coil through a magnetic field. It is important to note, either the magnetic field may be held stationary and the coil moved through it, or the coil may be held stationary and the field moved. Now that we've reviewed the basic principles of magnetism, electromagnetism, and electromagnetic induction, we will begin to look at the types of electrical currents and how they are generated. First, direct current is a current that flows in one direction. The purest form of direct current is produced by chemical batteries, such as your car or flashlight battery. A chemical reaction causes the generation of pure DC current. Pure direct current has a constant value or magnitude with respect to a time base. A varying direct current varies in value or magnitude with respect to a time base. When these variations occur at regular intervals, going from 0 to some higher value and then decay to 0, the effect is termed pulsating direct current. When the variations are recurring at regular intervals but never decay to 0, they are termed ripple direct current. An alternating current is an electrical current which flows first in one direction for a given period of time and then in the reverse direction for an equal period of time, constantly changing in magnitude. The shape of an alternating current is that of a wave. The most common and important AC wave shape is the sine wave, named after the graphic curve it follows. Alternating current builds to a maximum positive value in one direction, decays to 0, and then reverses and builds to a maximum negative value in the opposite direction and returns to 0. A cycle is the pattern from 0 to maximum positive, back to 0, down to a maximum negative, and back to 0. The length of time to complete one cycle is called the period. Frequency is the number of cycles completed in a given length of time. The number of cycles occurring in 1 second is given the term Hertz. For example, 60 cycles per second would be referred to as 60 Hertz. AC current has become the most common form of electricity available in the world. It is very important to note that electromagnetic induction, the movement of a coil through a magnetic field, produces alternating current, AC. However, there are many applications that require DC power, such as an electromagnet itself. So you may ask, how do you convert AC current to DC current? First, for applications demanding large amounts of DC, an AC motor is used to drive a DC generator. The second, and by far the most often used methods, is rectification. Rectification is defined as the process of electronically converting alternating current to direct current. This occurs when a device called a rectifier is inserted into the electrical circuit, permitting the current to flow in one direction only. Today, modern rectifiers are solid-state diodes and are usually constructed of germanium or silicone. This illustrates the electrical symbol for a diode. Notice the current flow direction in relation to the arrowhead. Current attempting to enter the other direction is blocked. Only current in one direction is allowed to go through. A rectifier is actually an electrical check valve. The rectifier will allow flow in one direction, but will block flow in the opposite direction. This simple schematic illustrates half-wave rectification. Notice, we have a generator connected through a rectifier to a load. During the first half of the cycle, the current freely flows through the rectifier and the load. But as the second or reverse half of the cycle attempts to enter the rectifier, it is blocked. A graph showing the results of half-wave rectification would look like this, with the bottom half of the sine wave clipped. This is called half-wave rectification, as only half of the sine wave is used. However, full-wave rectification is more commonly used. This schematic is an illustration of a full-wave rectification bridge. In order to really appreciate the mechanical aspects of an alternator, it is important to recognize its basic components. A clear understanding of these components will prove very valuable when attempting to distinguish between the different types of alternators. We'll start with an armature winding. These windings consist of coils or groups of coils into which an AC voltage is to be induced or generated. The bearing carriers, or bearing brackets, or end bells, is the structural member of the alternator that houses or carries the rotor bearing. It can also house other stationary parts. A conducting element constructed of carbon, graphite, or in some cases copper, is called a brush. The brush is used to maintain a sliding electrical contact between stationary and rotating components. Brush holders are devices used to house and support a brush or brushes. Collector rings or slip rings are rings usually constructed of copper, on which the brushes slide to provide electrical continuity between stationary and rotating components. An exciter is a device used to supply DC current, excitation, to the field winding of an alternator. A commutator is a device mounted on the shaft of a brush-type exciter that mechanically rectifies the alternating current generated in the exciter armature to DC. A commutator is simply a mechanical rectifier. A coil, or coils, wound around the field poles of an alternator through which the DC excitation current flows, creating a magnetic field, are field coils. The field pole is the part of the magnetic structure of an alternator on which the field coils are wound. The laminated core is a ferromagnetic core consisting of a number of thin steel laminations tightly compressed and welded or riveted together, forming a magnetic path. This is the core around which the coils of an armature or field winding are placed. The rotor is any rotating winding or element of an alternator. Any stationary winding or element of an alternator is called the stator. A rectifier assembly is an assembly consisting of rectifiers, diodes, heat sinks, terminal lugs, or strips mounted on a board or ring. A rectifier assembly can be either stationary or mounted on an alternator shaft and rotated. Now that we've reviewed the basic components, you will have a better understanding of the different types of alternators as well as alternator fields. There are two types of alternators, the revolving armature and the revolving field alternator. The revolving armature alternator has a stationary field and an AC voltage is induced in the revolving armature winding. AC power is supplied to a load by way of brushes and slip rings. In the revolving field alternator, the armature winding is held stationary while the field is rotated and power supplied directly from leads from an armature winding. There are two types of alternator fields: permanent magnet fields and electromagnet fields. A permanent magnet field uses a permanent magnet to provide the field necessary for induction of current in the armature winding. A permanent magnet alternator, while very cost-effective, has the disadvantage of having its field strength, or flux density, at a fixed level. Thus, voltage regulation tends to be poor. The electromagnetic field uses an electromagnet to provide the magnetic field. The advantage of this type field is that the flux density can be controlled by varying the amount of DC current supplied to the field. The disadvantage is that this type field does demand an external source of DC current to start and maintain the magnet field. So far, this presentation has concerned itself with the theories, principles, and components of basic alternators. The next section will deal with taking these areas and applying them to basic alternator operation. Here again we have a basic illustration of a simple revolving field alternator. With this type alternator, the armature coils remain stationary and the field revolves. Notice here the position of the revolving field to the stationary armature coils. In this position, there is no cutting of lines, therefore no current being produced. On a sine wave graph, the dot illustrates the position of current in relation to the position of the revolving field. Now, as the field, rotating in a clockwise direction, enters the armature coil, cutting of lines of flux starts. Notice the movement of the graph. In this position, we have maximum cutting of lines. This is the peak position for current flow, as illustrated by the graph. As the field continues to rotate, we see less lines being cut, therefore a reduction in current flow. Until again, the field has reached a point of no cutting of lines and no current flow. But now, as the field continues around, it enters the second half or negative side of the cycle and continues to build to a maximum negative current flow. Again, the field starts to move out of the coils and the current starts to decay until the field reaches the end of the cycle, where again no lines of flux are being cut. During the last few minutes, we have reviewed the basics of understanding generator operation, its principles, and its components. It is our hope that this information will have been helpful as you continue to expand your knowledge in the world of electrical generation. The concepts and principles we have just reviewed will prove very helpful in your capacity of operating and maintaining your Lima generators. Your Lima generator properly installed will give you years of service. That's the sound of Lima. Lima energy at work. Day after day, Lima energy products at work around the world. finest name in generators in the world, is proud to present this presentation designed to help further your knowledge in the world of electrical generation. LIMA's dedication to training, coupled with the highest quality standards possible, have together earned a reputation for reliability and long life no other manufacturer can touch. This presentation is the second in a series to help you better understand generators. First, we will review the revolving field stationary armature alternators with a focus on stationary armature construction and principles. Second, we'll deal with single and three-phase power. Then, 1 and 2 circuit armatures, and finally, lead terminal identification. These 4 areas are instrumental in your training as a prelude to generator construction, so sit back, relax, and we'll get started. As you know, there are 2 types of alternators: revolving field alternators and revolving armature alternators. Revolving armature alternators have one major mechanical disadvantage: slip rings and brushes. These slip rings and brushes themselves have 2 major disadvantages. Number 1, they wear out and must be replaced periodically. And number 2, they are limited to the amount of connection options. The revolving armature alternator is totally unsuitable for larger units, whereas the revolving field alternator is ideal for units over 5,000 watts. The revolving armature alternator can be cost-effective in units of 5,000 watts or lower, but they do have the disadvantage of frequent maintenance and repair problems which increase in larger units. Revolving armature alternators are generally not reconnectable due to difficulties in making connections to the slip rings and holding extra leads in place while the shaft is rotating. The revolving field alternator is somewhat more costly initially, but does not have the maintenance and replacement costs of the revolving armature alternator. Now, here's where LIMA comes in. All LIMA generators are revolving field alternators. There are no slip rings or brushes, and all output leads and connections are stationary. Revolving field simply means the field rotates and the armature is stationary. Let's take a closer look at a stationary armature and review its construction and principles. A stationary armature assembly consists of 2 major components: the armature core and the armature windings. The armature core is constructed of thin laminations of electrical grade steel, tightly compressed and either welded or riveted together to form a core. The core contains slots to accommodate the coils of the armature windings. The armature windings have a number of individual coils consisting of multiple turns or loops of conductor wire, usually copper, that are inserted into the armature core. They are the coils that carry the current generated by the alternator. Each coil has a start and finish wire. These wires are used to connect 2 or more coils in pairs or groups. The connecting coils are then either connected in series or parallel. Series connection is tying the finish lead of one coil to the start of another coil. In a series connection, voltage is figured from the start of the first to the finish of the last and equals the sum of the voltage of each coil. However, since the current must flow the length of all of the coils, the current capacity of a series of equal coils remains that of a single coil. Parallel connection is when the start leads of both coils are tied together and the finish leads are tied together. If the coils are identical, the voltage measured across the parallel coils is the same as one coil. However, since each coil will carry its full current capacity, the total current carrying capacity is the sum of capacity of each coil in parallel. It is sometimes necessary to center tap a coil. This is done by attaching a lead to the middle or center turn of a coil. The voltage is measured from the center tap lead to either the start or finish lead and is equal to 1/2 the voltage end to end of the entire coil. The center tap is similar to the series connection of two equal coils. Following a diagram, the winder places the individual coils comprising the winding into the core slots with various insulating materials. Once the coils are inserted in the slots, the individual coil ends, referred to as the start and finish wires, are grouped together according to the specific instructions, and the load leads are then connected. The load leads are heavy cable leads that are evenly connected to the terminals. With the exception of the load leads, the entire wound core and coils are then given 2 or more coatings of insulating material. It is now time to enter the second section of this presentation, dealing with single and three-phase power. As you now know, the concept of single-phase power is quite simple. After all the armature windings are in place, they are simply connected together to form one large coil group. And as the revolving field rotates, an electrical voltage is produced in this coil. For illustrative purposes, imagine the coil group at a 12 o'clock or 0-degree position. But now, three-phase power is quite different and somewhat more difficult to understand. In order to understand a three-phase alternator, we'll again go back to the single phase for a moment. The field of an alternator has a north and south pole. As the field rotates, the lines of flux move through the armature winding and produce a current. The single-phase power consists of a single voltage and or current sine wave of 360 electrical degrees in length transmitted over a single line. Since electricity only flows in a complete circuit, single-phase power must have two lines coming from the source to complete the circuit. Three-phase power is three separate and complete coil groups spaced 120 electrical degrees apart. Three-phase power uses three transmission lines, usually designated Phase A, Phase B, and Phase C, or Line 1, Line 2, and Line 3. The 120 electrical degrees separation of phases maintains the balance in the system. When one phase has a voltage value of 0, the other two phases are equal in magnitude, or 86.6% of their maximum value. These two phases are also of opposite polarity or direction. The voltage measured between the two phases is 173.2% of the maximum value of one phase. The sum of two phases at 86.6% of their maximum value equals 173.2%, or the maximum value of one phase times 1.732, which is the square root of 3. Remember, a single-phase armature winding is pictured as a single large coil located at 12 o'clock. Regardless of the number of coils interconnected by the winder into a coil group, the entire group takes on the characteristics of one large coil positioned in one place in the core. Thus, one coil, single phase. Now, three-phase armatures have one coil group per phase and are termed single circuit armatures. Single circuits can have either low or high voltage, but not both. Many specifications require alternators to be reconnectable for either high or low voltage. An example would be a 40 kW, 50 kVA 60 Hz alternator to be connectable for either 240 volts or 480 volts three-phase. Since this is not possible with single circuit armatures, a two-circuit armature is necessary. To achieve two circuits, each phase coil group is split into two equal phase coil groups, and all four leads, 2 starts and 2 finishes per phase, or a total of 12 leads for all 3 phases, brought out to the connection box. Connecting 2 coils per phase in parallel provides a low-range output voltage. Again, single circuit may be either low or high range, but not both. Two circuit is reconnectable by using paralleling coils for low range or seriesing coils for high range. Let us now proceed to our fourth and final topic, lead terminal identification. Alternators manufactured in the U.S. usually follow the National Electrical Manufacturers Association standard NEMA MG1 for making lead terminals. Leads are given a number and a prefix letter. Armature leads have a prefix letter T, and field leads a prefix F. The NEMA terminal marking system is single phase, single circuit, single phase, two circuit, three-phase, single circuit, three-phase, two-circuit, high range, and three-phase, two-circuit, low range. Note that this system has a clockwise rotation going from top to bottom. Phase A is in line 1, Phase B in line 2, and Phase C in line 3. So, T1 is always in line 1, T2 in line 2, and T3 in line 3. We now have completed our review of revolving field and stationary armature alternators, single and three-phase power, one and two circuit armatures, and lead terminal identifications. We hope your expanded knowledge will help you make better use of the finest generators in the world, Lima generators. Produced by Lima Electric Company, Lima Energy Products, a division of Conduct. This presentation is the third in a series to help you better understand generators. At this stage, you have already reviewed electrical fundamentals an introduction to alternators and their component parts, and the basics of single and three-phase alternator armatures, including design and construction, output load leads, and the NEMA lead identification system. This presentation will focus primarily on the methods of external connection of single and three-phase alternators. Before we begin, let's remember that the standard voltage for single-phase 60 Hz systems is 120 volts, 240 volts, or a combination of 120 to 40 volts. Although there is no universal standard frequency for alternating current, 50 or 60 Hz are the most frequently used worldwide. So we usually refer to 60 Hz systems in this presentation. Let's begin with single-phase 2-lead alternators. This type unit is usually constructed with a single circuit armature with 2 output load leads. These machines produce a single voltage and may be designed for either 120 or 240 volts. Some units are designed to produce a particular non-standard single-phase voltage such as 480 volts. Units such as these are generally designed with 2 load leads. Single-phase 3-lead dual voltage alternators are similar in design to the 2-lead alternator. The difference is that the 3-lead alternator brings out an additional neutral lead. With a third or neutral lead, the voltage from either load lead to the neutral lead will be 1/2 the voltage line to line. Thus, if the total voltage is 240 from T1 to T4, the voltage from either T1 or T4 to the neutral lead, TO, will equal 120 volts. We now come to the most commonly produced type of single-phase alternators. These are the single-phase 4-lead reconnectable alternators, which are much more versatile than the 2-lead or 3-lead alternator. The single-phase 4-lead unit has a 2-circuit armature, usually designed as 120-volt coil groups. When connected in parallel, the unit provides 120-volt 2-lead service. When the unit is connected in series, it may be either 2-lead 240-volt or a 3-wire dual voltage machine with the load leads affixed to the series connection as a 3rd lead. So a single-phase alternator may have 2 leads or 3 leads, including a neutral lead, or 4 reconnectable leads. Obviously, the 4-lead alternator offers the most flexibility and therefore is the most often used. Let's now move on to 3-phase alternators. You'll recall that a 3-phase alternator has its coils grouped into 3 separate independent coil groups. An armature with any one of these coil groups would be a single-phase unit and could be loaded in that manner. Since each of the 3-phase coil groups are independent of each other, each may carry its own individual load. Each phase is designated by letter: Phase A, Phase B, or Phase C. For single-circuit armatures, each phase is an independent coil group, so 6 output load leads are available to be brought out for external connections. 2 circuit armatures have 2 smaller coil groups for each phase. Since they are independent of each other and have 2 load leads per coil group available for external connection, 2 circuit armatures have a total of 12 load leads. they may be brought out and connected externally. Keeping the number of possible external connections in mind, let's discuss the method of three-phase connection. There are two methods for connecting a three-phase alternator: the Y, sometimes referred to as a star connection, or the delta connection, symbolized by the Greek alphabet character, or a triangle. Most three-phase alternators today are Y-connected. With this Y method of three-phase connection, the finished leads of each of the three phases are tied together. These tied finished leads form a neutral point, and the start leads become the three output load leads. A fourth or neutral load lead may be brought out from the neutral point and is usually designated TO. The neutral load lead may be either grounded or left above ground. If the neutral load lead is left above ground, the unit is said to have a floating neutral. The voltage generated in each phase of the Y-connected alternator, measured from any output load lead to neutral, is called line to neutral, phase to neutral, or phase voltage. Keeping in mind that there is a displacement of 120 electrical degrees between each phase. Therefore, the voltage measured line to line is equal to 1.732, or the square root of 3, times the voltage of one line, as you should remember from our previous program. The formulas for calculating the voltage in a three-phase Y-connected alternator are: A, line to neutral voltage equals line to line voltage divided by the square root of 3. B, line to line equals line to neutral times the square root of 3, which is 1.732. Where L to N, line to neutral, equals voltage line to neutral, then L to L, line to line, equals voltage line to line. Three-phase voltages are usually specified as the line-to-line or phase-to-phase voltage required. Frequently, however, both the line-to-neutral and the line-to-line values will be called out with the line-to-neutral first. An example is line-to-neutral 120 and line-to-line 208 with a slash in between. Let's look at a table listing the line-to-neutral voltages for a number of common three-phase line-to-line system voltages, 600 volts and lower. Note that when the system voltage is above 208 or 416 volts, the available single-phase voltage, line to neutral, will be higher than the standard 120 or 240. For example, note that for 240 or 480 volt systems, the line to neutral voltage is 139 or 277 volts. This is 15% above the normal nameplate voltage for most single-phase equipment. For this reason, when using Y-connected units for both single and three-phase loads, you must make sure the line-to-neutral voltage is not too high for the connected load. Three-phase, four-lead Y-connected alternators are internally connected, with the neutral or fourth lead brought out. In some cases, a 480-volt four-wire Y-connected unit will have two phases center tapped. This provides 240-volt single phase for input power for an automatic voltage regulator. Three-phase 10-lead wire Y-connected alternators are two circuit units with the finished leads of one of the two coil groups of each phase tied together with the 10th or neutral lead brought out. These units are then reconnectable for low voltage range when connected in parallel, or high voltage range when connected in series. Remember, with Y connection, the finished leads of each of the three phases are tied together to form a neutral point. We shall now proceed to delta-connected three-phase alternators. The delta connection has the start lead of one phase coil group connected to the finish lead of the second coil group, which is connected to the finish lead of the third group. The connections form a triangle, with each of the three output load leads secured to its respective corner of the triangle. In a three-phase, three-lead-wire delta-connected alternator, connections are made internally in this manner. The voltage is measured from line to line, as in one phase, which we discussed previously. Three-phase, four-lead-wire alternators with delta connections have one of the phase coil groups center tapped, with the center tap brought out as the fourth lead. The fourth lead is not a neutral lead in a delta unit. There is no neutral in a delta connection. If the voltage for each phase of a delta-connected alternator is 240 volts, the center tap lead to either adjacent load lead can provide 120 volts single phase. 6-load lead, three-phase alternators may be connected with either a delta connection or a Y connection. 6-load lead alternators can also be reconnected to provide total single-phase output, as we will discuss in a few minutes. 12-lead alternators may also be connected Y or delta three-phase or for total single-phase output. Since these alternators are two circuit units, they can also be connected for low voltage in parallel in a delta or Y or series high with delta or series with Y. Now, let's see how 6 and 12 load lead alternators can be connected for total single-phase output. You'll recall that each phase coil group can be loaded as a separate and independent phase. Therefore, if the load is divided into three balanced circuits, each phase can power one circuit and the unit left connected as a three-phase unit. However, you must remember that the current demand on any one circuit cannot exceed the full load current of the alternators. The safest method to avoid overloading is to install a three-pole circuit breaker. You can then break down the load into three circuits on the load side of the circuit breaker. Three-phase armatures may be reconnected to a single-phase armature if all the phase coil group leads are brought out to the connection box. This connection is called a single-phase zigzag connection or an open delta connection. A 12 lead wire alternator may be zigzag connected for 480 volts single phase. If the phase voltage in a zigzag connection is 120 volts, the current carrying capacity of the armature windings is the same as when it is connected for 120 to 208 volts in a three-phase Y connection. As you can see, a three-phase generator connected in a zigzag connection becomes a single-phase generator with 2/3 of its three-phase capacity. We have now completed our review of the methods of connection of single and three-phase alternators. We have discussed single-phase and two-lead alternators, single-phase, three-lead alternators, single-phase, four-lead reconnectable alternators connected for low or high voltage. We have covered three-phase alternators with single-circuit armatures and two-circuit armatures. You can now recognize Y or star connections with a neutral lead, as well as delta connections where additional leads are not neutral. You also are aware that both 6 and 12 lead alternators may be connected for total single-phase output as well as Y or delta connections. It is the hope of Lima Energy that this review has been helpful to you and that it will enhance your ability to make optimum use of the finest generators available. Lima generators, designed and built for you by Lima Energy Products, a division of Condec.
Lima Energy Products, the finest name in generators, presents Part 4 of the series Understanding Generators. This presentation will focus on frequency, frequency regulation, excitation, voltage regulators, and voltage regulator accessories. Again, regulated units are designed to compensate for load or changes in load and load power factor. For this reason, they are not as susceptible to poor regulation as a result of load factors. Let's start with frequency and frequency regulation. The frequency of the alternating current produced by any alternator is dependent upon the number of magnetic poles constituting the field of the unit and the speed of its shaft rotation, RPM. An even number of poles are always used to construct the field, with the total number determining the number of cycles produced by each complete revolution of the rotor. For example, a two-pole field will produce one complete cycle per revolution. A four-pole field produces 2 cycles per revolution. A 6-pole field, 3 cycles per revolution, and so on. Since frequency is indicated in hertz, or cycles per second, and rotative speed in revolutions per minute, calculations for alternator frequency can be made with this formula. Frequency in hertz equals number of poles times RPM divided by 120. RPM equals hertz times 120 divided by the number of poles. While there is no such thing as a standard frequency for alternating current, various industries have standardized specific frequencies for their own applications, such as 400 hertz for the aircraft industry. 60 and 50 hertz have emerged as the 2 most popular frequencies worldwide for commercial and residential use. Most of North America has a 60 hertz standard commercial frequency, while 50 hertz is the standard for commercially available power in Europe. Take a look at the table of synchronous speed for 2, 4, 6, and 8-pole alternators. Note that the greater the number of poles, the lesser the rotative speed to obtain any desired frequency. Frequency regulation, unlike voltage regulation, cannot be controlled by an alternator or its accessory equipment. Regulation of frequency is purely a function of the alternator's prime mover and its speed governing system. Governors are available in a wide variety of devices, from simple flyball types to very sophisticated electronically controlled systems. The degree of accuracy can range from a regulation of plus or minus 5% to plus or minus 0.5% or better. Now let's briefly review the basics of electromagnets, because the rotating field of a brushless alternator is in fact an electromagnet. An electromagnet consists of a soft iron laminated core around which the field coils are wound. During part 1 of this series, we saw how a direct current flowing in a coil produced a magnetic field. By varying the magnitude of the DC current, we also varied the strength of the field. Direct current flowing in a field winding is termed excitation. The source of this DC current, or excitation, is called the exciter. There are several types of exciters, including the brush-type exciter, which is actually a small DC generator. They can be either external to the main alternator or can be incorporated within the construction of the main alternator. Static exciters, having no rotating parts, essentially employ transformers and rectifiers to convert AC current to DC current for excitation. And brushless exciters, which are small revolving armature alternators incorporated within the construction of the main alternator. The AC output of the revolving armature of a brushless exciter is rectified by means of a rotating rectifier assembly mounted on the shaft. This DC excitation is fed directly to the main field windings by means of the two main rotor leads, thus eliminating the need for brushes and slip rings. As the AC output current of a brushless exciter is rectified to DC, there is no need to limit its frequency to 50 or 60 Hertz. In fact, most manufacturers of 4-pole 60 Hertz alternators construct the exciter field with 6 or 8 poles producing 90 or 120 Hertz to give a smoother DC output. And to take advantage of the fact that the higher the frequency, the more power that can be taken from a given volume of active material. There are two basic functional types of automatic voltage regulators. The first, and most common, senses only the output voltage of its alternator. By varying its output, this regulator maintains or attempts to maintain the alternator's terminal voltage at some preset level or value, regardless of any variation in the alternator rotative speed or frequency. In previous presentations, we have covered the fact that the normal reaction of any alternator is to have its output voltage vary directly with speed. Thus, if the prime mover is operating at some speed lower than rated synchronous speed, the alternator's natural voltage will be low. However, with this type of voltage sensing only regulator, under conditions of low frequency, low speed, it will increase its output to maximum if necessary in an attempt to drive this natural low voltage up to the preset level or value. This action could, and often does, result in premature failure of the regulator and or some other component of the alternator's excitation system if low prime mover RPM is maintained for a period of time. The second type of automatic voltage regulator is designed to not only sense the alternator's terminal voltage, but also monitor its frequency, and will maintain the unit at the preset voltage only when it's operating at the rated frequency. If the rotative speed is either increased or decreased, this regulator will cause the output voltage to increase or decrease in proportion to change in speed. This type voltage regulator is classed as volts per Hertz regulator. By varying voltage with frequency, this type regulator will tend to eliminate the problems of under-frequency operation as associated with voltage sensing only units. The series boost system utilizes the principle of ferroresonance to provide a source of regulated voltage to the voltage regulator. The power for the system is provided from a voltage source and a current source. The voltage source is obtained from the output of the alternator, while the current source is obtained from line current via the current transformer. In operation, this system supplies power in the form of a constant AC voltage to the automatic voltage regulator. The current boost system consists of a static control rectifier assembly and a power current transformer. The control assembly typically receives AC sensing voltage input from the main alternator and current input from the power current transformer, similar to the series boost system. The difference is that rather than supplying a constant single-phase AC voltage to the automatic voltage regulator, the current boost system is designed to provide DC current directly to the exciter field. Although manufacturers of these systems have different schemes to initiate and control output DC current, the basic design usually incorporates a form of voltage comparator circuit to suppress output to the exciter field until the main alternator's voltage is depressed to a preset level. Once that level is reached, the controller will allow controlled DC power to flow directly to the exciter field. Another advantage of an excitation support system is that it can supply to the automatic voltage regulator sufficient power to drive the exciter to its ceiling and enable the alternator to sustain up to 300% short circuit current flow. You'll remember from our discussion of electromagnetic induction that if the strength of the field or flux density and the rotative speed are held constant, the magnitude of the induced voltage is directly dependent on the number of loops of wire in the armature coil or coils. Engineers often design several alternators of the same output capacity to have different output voltages by using identical fields and exciters, merely changing the number of loops in the armature winding coils. Many factors affect the magnitude of the output voltage of an alternator, but they are designed to produce a specific, predetermined voltage. Varying the conditions of load, rotative speed, and flux density can and will directly affect the output voltage of the machine. Regulation of the output voltage of electromagnetic field alternators is obtained by controlling and coordinating the DC excitation supplied to the main field windings by the automatic voltage regulator. You'll remember most of these type alternators employ an external automatic voltage regulator, which senses the output voltage and compares it with the preset referent voltage. It then corrects the exciter output as necessary to maintain the output voltage of the main alternator at some level or preset value. Alternators designed with external voltage regulators are termed externally regulated alternators. In these cases, The voltage bandwidth is expressed as a percent plus or minus a predetermined voltage value within which the output of the unit will be maintained. This can also be considered to be the degree of accuracy of the voltage regulator or voltage regulation system. Three major factors, temperature, speed, and load, affect voltage and voltage regulation, with factor 1 being the temperature of windings. Copper wire used in the manufacture of alternator windings is an excellent conductor of electricity, but has some resistance to the flow of current. This resistance to current flow will increase or decrease in direct proportion to the temperature of the wire. For example, the warmer the wire becomes, the greater its resistance to current flow. When current flows in the windings, this resistance will cause a warm-up of the windings in direct proportion to the amount of current flowing in the winding. Therefore, when a winding is loaded to its maximum rated current carrying capacity, its temperature increases to maximum, and thus its resistance will also be at maximum. The increased resistance from no current flow or no load to rated current flow or full load will cause the output voltage of the winding to drop gradually as the windings warm up to operating temperature. This drop in output voltage is referred to as temperature drift or just drift. This drift can have a substantial effect upon voltage regulation of alternators which are not equipped with an automatic voltage regulator or some form of temperature compensation circuitry. For these units, the formula previously given for voltage regulation should be changed to include temperature in this manner. This drift is not a significant factor for externally regulated alternators, as the voltage regulator automatically compensates for the drift, since the voltage regulator will compensate for any change regardless of cause. A second factor affecting voltage is rotative speed of the alternator's shaft. If the non-regulated or self-regulated alternator's prime mover is equipped with a good governor, the resulting system, alternator and prime mover, voltage regulation should be fairly good. However, if the prime mover's governor or speed regulating system allows a broad speed regulation bandwidth, the resulting system voltage regulation could be poor. Externally regulated units will give a better performance with poor speed governing, since their voltage regulators usually can compensate for speeds that range from plus or minus 5 to 8% of nominal or rated speeds. A third factor affecting voltage regulation is the magnitude and nature of the connected load. We hope you found this presentation helpful. The Lima Energy Series, Understanding Generators, is produced and developed for our customers and their employees as part of our continuing effort to provide the best product and service in the industry.